So today we're happy to have Fabian Schmidt from Max Planck Institute for Astrophysics in Garching, and he's going to tell us about probing substructure with stellar streams. So, yeah.
All right, thanks, Giovanni. Thanks for inviting me, and I'm excited to talk about something that you might have not heard from me before about. So very likely, actually, not have heard from me about, which is a small-scale structure, namely looking at what cold dark matter does on scales within halos. So any cold dark matter scenario predicts a whole hierarchy of structures down to some minimum mass that could go from all the way down to Earth mass size. And to me, this is interesting because it's probably the main prediction of the cold dark matter framework that hasn't been verified so far, right? So we've verified that everything is consistent with cold dark matter on large scales, on megaparsec scales, and even with galaxy formation, it seems very much consistent with CDM. But what we haven't verified is what goes on smaller scales. So really what we expect to see is that there should be a whole hierarchy of objects with some mass function, power law mass function, that goes up to some, other end, the cutoff, should go to some minimum mass, depending on what actually the dark matter is. So we believe that in the regime where we can neglect all self-interactions of dark matter, the mass function should scale roughly like m to the -2, so kind of a scale invariant mass function, and some low mass cutoff, which could be anything from 10 to the 8 solar masses down to 10 to the -6 solar masses. And that the scale of that cutoff could tell us something very interesting about what dark matter actually is. But getting to that cutoff, actually detecting it might be totally out of reach. Again, I'm mostly just motivated by finding these things, this definite prediction of the CDM framework that we haven't seen so far. And there could also be, this thing could also look completely different if we look at non-standard. So this is standard CDM. But things could also look different if we look, for example, at superfluid dark matter or fuzzy dark matter. Then this structure could look quite different because of their very different properties. So the problem is, how do we search for these things? They are fairly diffuse. They're, assuming dark matter is not primordial black holes, these substructures will be quite diffuse. And so one way is to rely on some non-gravitational interactions. So for example, annihilation signals. But of course, we don't know if dark matter actually interacts with any relevant strength with non-gravitational interaction. So what we're really looking for is a gravitational search for this, purely gravitational search for these substructures. And the approach that I'm going to talk about today is to look at cold stellar streams inside the Milky Way halo and to see if those can tell us about substructure. So cold streams, where do they come from? Well, if you have a very low mass dense object, for example, like a globular cluster that orbits the Milky Way center on an eccentric orbit. So here's the center of the Milky Way halo, and this globular cluster orbits on an eccentric orbit. What happens is that due to the fact that the tidal forces here are quite significant, the least bound stars in this globular cluster get stripped, and they begin to move outward along this orbit. And they move not exactly along the orbit, but very close to the orbit. And they form basically a one-dimensional manifold in phase space. And this is due to the fact the way the Milky Way halo, the way the smooth galactic potential halo is structured. This leads to them forming a thin stellar stream. And this means that the typical velocity dispersion along this perpendicular to the stellar stream is very small. It's just of order of the intrinsic velocity dispersion of this original globular cluster. So the velocity of the entire globular cluster of the stream is of order the virial velocity of the halo, right? So 300 kilometers per second, say. But the velocity dispersion is much smaller. It's a few kilometers per second if you have a really low mass progenitor. Okay, so that means these things are quite sensitive to disturbances that even give them a very tiny velocity perturbation. So due to that fact, and due to the fact that due to other effects of the physics that we'll get to, they are actually a very interesting probe of substructure within this smooth halo. Okay, so let's then go to stream encounter. So, I mean, you know, just the streams themselves are a very interesting galactic dynamics problem, but I want to go straight, given the time, I want to go straight to the encounter. So moving away from what the stream does in a smooth potential. So now let's kind of zoom in at the sketch that I showed before and kind of look at just a segment of the stream. Let me try to sketch this. I'm going to try to make the stream star semi-regular to make it easier. So if I zoom in, the stream is approximately a straight line, right? So I can just assume the stars are distributed along a straight line in real space. And now suppose I have a substructure, some not so massive object, but sufficiently massive object moving by the stream, right? So it's going to move by, and what it's going to do, it's going to accelerate the stars on this side of the stream. It's going to accelerate in this way, very roughly, perpendicular to the trajectory, and the stars here will be accelerated this way, right? So naively, one would now think that okay, so due to this acceleration pattern, we will now see an overdensity forming, right, in the stream due to this encounter. But in fact, what happens is that so if we call this if we call the velocity of the stream stars, approximately assume they have the same orbital velocity, which they do, I'll call that V, then this part here has a delta V. This star here gets a delta V parallel to the stream itself that is negative, right? It's being decelerated. This one is being accelerated, right? So what actually happens is that for a star with a delta V parallel greater than 0, that means it actually gets angular momentum, right? This is V is at some angle with the radius vector to the center of the orbit. So delta V parallel greater 0 means that delta L is greater 0. So we get a positive angular momentum imparted. And that means the star moves to a larger radius, right? The star after this perturbation will be on a new orbit that is on a slightly greater radius. And so that means it will have a lower period in potentials like the Milky Way's halo. And that means it will actually start lagging behind the rest of the stream. So actually the star being accelerated this way, it will actually begin to lag behind. And conversely for this star, it will go ahead because it has gets less angular momentum, goes on a lower orbit, and hence goes ahead. Moves behind due to larger orbital radius. So that's one of the peculiar things about galactic dynamics. So the velocity perturbations perpendicular to the orbit, which don't change the angular momentum, behave completely differently. So there you basically just get an oscillatory motion, an epicycle that the star oscillates around the orbit of the stream. And those, of course, are not so interesting to us. So so what is the big point about this? What you can see is that if we have a sufficiently massive object passing through, we will actually form a gap in the stream because all the stars on the left side will be moved, will start moving, bunching up. So what you will get is something that now stars on the left side will be bunching up, and on the right side, they will also be bunching up. Long after this perturber has passed, right? So apart from the fact that due to small velocity dispersions, streams are sensitive to low mass perturbers, to small velocity kicks, the other neat thing about them is that they kind of retain the memory of past encounters in form of these kinds of gaps. Okay, so stream gap, and there's a whole literature going back to the 90s proposing stream gaps as a way to look for substructure. Now, as you can imagine, this is a very strong perturbation in the stream density. So this happens only for sufficiently massive perturbers. So if we want to now push this method to look for a smaller substructure, which is given the mass function that I showed earlier, right? Smaller substructure is much more numerous. Sorry about the delay here. Is much more numerous, so you have potentially more signal if you're able to go to much lower masses, right? So so what we did in our paper is move to a totally different regime, and we wanted to study the weak encounters due to much smaller perturbations in the stream. By the way, feel free to interrupt if there's questions already.
I had one question. I'm a little concerned with your idea of having gaps in streams. I mean, as you said at the start, the stream is a one-dimensional manifold in phase space, and if there are Hamiltonian perturbations on it, it always has to stay a one-dimensional manifold. That is, it can be distorted, but you can't cut it.
Mm-hmm.
So how do you make a gap in a one-dimensional manifold?
It's true. It's strictly speaking, it's an underdensity. So really, if you look at the one-dimensional stream density, it would be something like this, and not go to absolute zero. It'll probably it will probably drop to some finite. I mean, it will definitely drop to some finite value down here. And so, for example, for the stars that sit right at the perturbers where the perturber passes through, there is no delta V parallel. So they will basically stay at the same azimuthal position and just oscillate, do some epicyclic oscillations. So it's true, there will definitely be some density here.
Okay, thank you.
But observationally, of course, we sample this phase space distribution, this phase space submanifold discretely, whether we see stars. And so empirically, there will be some gap of some certain width. So, right, so let's go to the regime that we studied in this paper with Sen, who was a postdoc at MPA, by the way. So we want to study the regime where we don't have one massive interaction with a big perturbing object, but lots of small interactions. And so if you think of it that way, it's you can think it's natural to think about it as a diffusive process, lots of small velocity kicks which make the stars on the stream diffuse in phase space. And for that, we kind of used tools and skills we have developed in the regime of cosmology as a field in the last many decades. So we naturally split things into a background and perturbations. So the first thing is that we write the perturbing density. So the background, or the, not the stars, but the density that's perturbing the stars, as some mean density, which we treat as constant for the time being. If I have time, I'll get to the generalization at the very end. Right. So now the mean density rho bar of smooth distribution will not do anything to the stars, but these perturbations, these fractional density perturbations, will lead to gravitational potential perturbation, which in turn impart a velocity kick. So then we just use Newton's law. V dot is minus grad phi, and the Poisson equation. The plus phi is 4 pi g rho bar delta. So this is the perturbing potential, right? This does not contain the smooth part of the Milky Way halo, just the perturbers. And if you combine those two, then you can integrate the equation of motion, assuming that during the encounter, the star still moves roughly on a straight line. So we basically assume the encounters are relatively quick compared to the overall motion of the stream, which for the scales we will be looking at is a good approximation. So then the velocity kick imparted on a given star at a given location as a function of time t can be written as it's all linear. Then, if we assume the stellar motion is a straight line, it's all linear and can be written simply as a transfer function. So this density perturbation delta of k in Fourier space convolved with the velocity transfer function, which depends on the velocity of the perturber. Okay, so here we already, so this looks very simple, right? Basically, our delta V, sorry, I have to, of course, the exponential. So this is something, a type of equation we're very used to in cosmology. Basically, you have a transfer relating one Fourier space field linearly to the desired field. One subtlety here that we immediately encounter is that this only works as long as we keep the perturbing velocity, the velocity of the perturbing density field fixed. So here I basically assume that the perturbers that make up the field delta are all move with the same velocity u. So in the end, obviously this is not correct. In the end, we have to incorporate the velocity distribution of the perturbers by, in the end, integrating the whole thing over d3u over the distribution function of perturbing velocities. So what we're doing here is we're assuming a separable ansatz for the phase space distribution of the perturbers, which is not, in principle, not essential to the method, but in practice, to make any progress, you have to make that assumption. And really, any other method developed for this problem simulation-based method has also approximated all the distribution function as separable. So we're not alone in doing that. So, okay, so let's move on. I'm not going to describe precisely how we do this integral because it's technical, but it can be done. So basically, morally, if we look at this equation, right? So now what we can do, we immediately can compute the statistics of delta V based on just the statistics of delta of k. In particular, what we can do is we take P of k, which is basically delta of k, delta star of k. let me put a squiggly here. We can take this and immediately transform it to P delta V, the power spectrum of velocity kicks imparted on a stream, and as a function of time. And it turns out that when you look on time scales that are much longer than an individual encounter, which is the case we're talking about, because encounters are millions of years, the age of the stream is 10 giga-years, so that's a good approximation. Then this power spectrum will scale simply proportional to t, which really just says that it's a diffusive process, right? It's a random walk, so the power spectrum, the variance grows proportional to time. And just for reference, we will be looking at, so the scales we want to probe with these streams is here, k is of order 10 to the 3 to 10 to the 4 inverse megaparsec, right? So quite small scales for us. For the cosmologists among us, of course, this is just 1 to 10 inverse kiloparsec.
There is a question by Matthias.
What's happening with the orbit of the stream? I'm confused. But why is this not some sort of integral along the orbit of the stream or something or other?
Why is what not a conserved quantity?
Sorry? No, what's happening with the orbit of the stream? Why the result is not dependent on the history of where the stream is in the galaxy?
It is. Yeah, it is. So we're looking here at an individual encounter, right? So this is still just this is just the velocity kick imparted on an individual star, right? So what happens with that star, and that of course depends on where the star is within the stream and within the Milky Way halo.
And you're assuming.
But so far it's just gravity, right? I mean, gravity in terms of really just giving a velocity kick to stars.
But when you translated the delta or your result in terms of a power spectrum, you're assuming translation invariance, for example.
Yes, that's right. So yeah, that's so I would get to that later, but let's be clear now. So here, the assumption is, so this approach definitely breaks down when you go to k that approach scales that approach the length of the entire stream, right? Then this whole thing approximating a segment of a stream as a straight line, it's assuming that all the stars have equal age along the stream, all that breaks down. So we are focusing on small segments of the stream, so k is much higher than the inverse scale of the orbit.
But even that, you might assume that it receives kicks when it's, I don't know, near the center or far away from the center, or some different amount of kicks as it goes, as it goes around the Milky Way.
Right. So in the end, what we have to do then is average over the radial range of the orbit and average over the position in the orbit that a given star gets a kick. So because in the end, we're interested in things are average over multiple orbits of the stream. So in the end, we're interested in a stream average, in an orbit average. But I'm not even at the density yet of stars yet, right? I'm still at the level of velocity kicks. Okay, and those are, of course, I mean, this expression is correct. It's just the equation of motion, right? So here we just assume that during the encounter, the star still moves on a straight line. Okay. Yes, so okay, so we can get P delta V, right? But this is not something that is observable because, first of all, it's hard enough to measure velocities of many stars, and second, we don't know what the original velocity was. So P delta V is not an observable. We want to get something that's observable, ideally, finally, the density of stars along the stream. And to get that, there are several subtleties that Matthias already alluded to. So let me describe this. I'm running severely out of time. But basically what we do is we use a Fokker-Planck approximation and saying that every star exhibits many of these small kicks. So it's basically, we write down the one-dimensional distribution function of stars along the stream, V, X, and T, and that obeys basically a diffusion equation. Diffusion equation in a local diffusion equation of real space, and so it's local. It's a local diffusion in velocity space. So this should be V, not nu. And basically, the constant C is just the time derivative of the velocity kicks themselves at the location on the stream where we're looking at the position X. And so this is really a coherent drift, and this is the diffusive part, and this is the time derivative of the variance of the velocity kicks. Okay, so now I really have to speed up, but basically what we do is we now separate then the distribution function into a homogeneous part, which is independent of the position along the stream and the perturbation, which we're interested in. And then we can actually solve, again, we obtain a linear equation that we can solve assuming that the unperturbed distribution is Maxwellian. And that essentially, cutting a significant story very short, is that the power spectrum of stars along the stream at a given scale k is basically a time integral with some kernel of the power spectrum of velocity kicks. Okay, and now here we have to actually incorporate, in this time integral, we have to incorporate the fact that where the velocity kick happens affects the actual motion drift of stars along the stream, which it goes into this convective derivative and several other complications. But I'm really running out of time, so I want to jump to the results. So basically, what we have is a semi-analytic prediction for how to compute this power spectrum of the stream density given a power spectrum of perturbers that went into the calculation of the velocity kicks. So we just need a given power spectrum of substructure, and we can calculate the power spectrum of the stellar stream density. And it basically is, again, a power law. So it's really very precisely a power law, because the mass function of substructure is just a power law. There's a cutoff at high k, which is due to diffusion. But that's at really high k, which are probably not relevant observationally. Let me put some units here. So here's 10 inverse kiloparsec, and here's 1. And then at low k, there is basically this regime is not really tractable because we here reach the scale of the entire stream. Here, in principle, things grow more slowly, so we can see it's still a growing regime, and the power spectrum becomes shallower. Yeah, I'm really give me 2 more minutes to describe one more thing, which is the time evolution. So what I showed here was the power spectrum, the stream density at fixed time as a function of k, which cosmologists are very used to. Now let's look at the power spectrum at fixed k, but as a function of time, because there things are slightly more interesting. Basically, when we start these calculations and integrate, we see behavior that looks like this. And we can explain where these 3 phases come from. Basically, in the intrinsic, in the early stage, it's pure growth because there's no initial density perturbations in the stream, and everything, as soon as you inject a velocity kick, it will produce a density perturbation that rapidly grows. That's not a very realistic regime in the real world because we see old streams. So here, the steady state regime is the more interesting one, where there's a balance between the continuous injection of density perturbations due to perturbers and the diffusion due to the intrinsic velocity dispersion in the stream, right? So you inject a density perturbation, but then since the stars have random motions intrinsically, the few kilometers per second I mentioned earlier, they diffuse out. And so here you have a steady state regime where the density is actually, the power spectrum density perturbation is roughly constant. And then eventually the velocity dispersion actually becomes dominated by stream encounters. And then those, as you continuously inject, the velocity dispersion grows, and that leads to a decay. So that that's the late phase, and that's basically what I showed here. So injection dominated diffusion. Okay, so just to, before I conclude, of course you might ask, well, great, it's a neat semi-analytic calculation, but does it have anything to do with reality? So what we did, what Sten did rather, it was to use this code called GalPy that was developed by Joe Bovey, which actually has stream particles, stars orbiting in a smooth potential, and then applies velocity kicks according to a given spectrum, mass spectrum of perturbers. And so it actually integrates the orbital equations for each star. It's quite expensive, but that we find really quite good agreement in the regime where the perturbation theory can be trusted, namely up to the regime where the perturbers actually dominate the velocity dispersion, then the perturbative treatment breaks down. But in this regime, which is the observationally relevant one, we find a very good agreement. So it seems like we really captured the essential physics with this. And so what's the use of it? Well, now we have a tool that's very versatile. You just need to give us a power spectrum of density perturbation, and we can compute the power spectrum of the stream. And so we can do forecasts based on alternative dark matter models, or we can push to much higher resolution than is possible with actual n-body type calculations and things like that. So I'm pretty excited about it and very happy to take more questions. Thank you.
Thank you, Fabian. So do we have more questions?
So this is a one-dimensional density.
Yes. Yes.
So I guess there is the related information of how the stream is getting wider. So the transverse direction, is that useful at all?
Yeah, I mean that's then you also need to incorporate the oscillations that happen due to perpendicular velocity injections. Yeah, yeah, it's definitely an observable we can calculate. What I'm wondering is the thing is, what happens is there is the stream becomes wider and wider as you go out, because the older stars have diffused further because they have been stripped earlier. So you have to take out that trend, which might make things a bit more. So you have an additional, basically, background degree of freedom that you don't know, which is the stripping rate of the globular cluster as a function of time. But maybe it's possible to get around that. I think could be interesting. Yeah. So what we definitely have looked at is velocity power spectra. So if you, not velocity kick power spectra, actual velocity power spectra, which you can get if you have spectra, right?
But here you also have this problem of the density not being uniform to start with, because of when, say, things get stripped when you're closer to the center or something like that, right? So you would still need to take this off. To take this into account.
Right, although that is pretty, I think that gets mixed by the, that gets mixed a bit because the stars drift along the orbit, right? So yeah, but it's I think for the young stars, that's definitely still a concern. Yeah. So for the part of the stream that's close to progenitor, there's going to be intrinsic density variations that, yeah, probably one should cut away that part of the stream.
There is a
But
question.
in general, I completely agree. Yes, we can calculate more observables with this approach quite straightforwardly. Yes.
There was a question by Scott.
Of course, there's also perturbations from the small scale structure in the baryons, molecular clouds, spiral arms, and so forth. Do you have a clean way of distinguishing when you see something, whether it's due to the dark matter or the baryons?
Right. Of course, that's an extremely important point in this whole game. So I think in terms of the power spectrum shape, it's going to be extremely difficult to disentangle, because you would really need to resolve, like basically find that the power spectrum is not consistent with just point objects, but you need to actually resolve the clumps, whereas the baryonic structure would be more dense. I think the power spectrum shape is very difficult. So the main hope is to look at streams that have different radial ranges, because the baryonics should obviously be much more concentrated towards the center of the Milky Way halo. So if you find structure in streams that are far out in the halo, then that will be more robust. Also, those that go through the disk versus those that have a pericenter outside the disk is a good distinguishing property. But in general, I mean, for this approach, it of course doesn't matter. The P of K should obviously include baryons in general, the P of K of perturbers that we put in. And we're actually measuring it now in hydrodynamical simulations that include feedback and everything. So full-fledged galaxy, high-resolution galaxy simulations that include the baryons to really see directly what is the effect of the baryons.
Okay, thanks a lot, Fabian. I think we will, yeah, thanks a lot. We can move to Nash. Feel free, Nash, to take the time that you would have taken anyway. So it's fine if we will be a few minutes late, I think. So we have then Nash from KCL in London, and he's going to tell us about new roles to the small scale universe.
Right. Hi, everyone. It's a pleasure to be here. Thank you for tuning in. Yeah, I'm very excited to tell you about a recent work that I did together with my advisor, Diego Blas, and our fellow collaborator, Julian Munoz. This work presents our first step in building a fast and versatile galaxy luminosity function pipeline to learn about the fundamental nature of dark matter. So the UV galaxy luminosity function has already been widely used in studies of the physics of galaxy formation and the astrophysical processes involved therein. But it turns out that the same data actually also provides us with a highly complementary handle on understanding some of the fundamental properties of the dark matter. In particular, in what follows, I will show how this probe can be used to measure the small scale clustering of matter. I'll start off with this figure, which gives a very rough overview of the current data sets we have as a function of the scale and redshifts that they cover. So most of our understanding of the properties in our universe is based on observations of the cosmic microwave background at redshift around 1000, and on a number of local universe probes that include Milky Way satellites, cosmic show surveys, galaxy surveys, and so on. The area that is enclosed by this black line shows when nonlinear corrections become relevant, and this, of course, makes some of the analysis here more complicated. But nevertheless, these data sets already show us a rich evolution of cosmic structures. It started off as tiny matter fluctuations at the time of CMB decoupling, that then hierarchically grew to become the observed large-scale structure today. They tell us that there is dark matter in our universe and that this dark matter is cold and collisionless at supergalactic scales. And that's almost it. There's still a whole lot we don't know about the dark matter. And this naturally means that we need to come up with new ways to search for its possible signatures. And one way of doing so could be to try to access scales and redshifts beyond those probed by the data sets shown here. Could be that some of the fundamental properties of dark matter have a more pronounced effect in this regime here. For example, if the dark matter is warm or fuzzy, or if there are dark acoustic oscillations involved, or simply that the modeling in this regime here is easier because you are further away from the deep nonlinear regime. And it is in this regard where the galaxy luminosity function comes into play. In essence, the first few generations of galaxies that populated our universe during the eras of cosmic dawn and reionization resided in dark matter halos that are much less massive than their counterparts today. So by assuming that the abundance of such galaxies indirectly track the mass function of dark matter halos, we now have a new handle on the physics of structure formation during an uncharted epoch. The good news is that the Hubble Space Telescope has been observing galaxies at high redshifts for decades now, and it means that we already have data that we can use. This data covers the redshift range 4 to 10, and of course, the James Webb Space Telescope has already been launched and will only further extend this redshift window to higher values. So simply speaking, at high redshift, galaxies contain young stars that emit in the UV part of the spectrum. This UV radiation gets redshifted due to the expansion of the universe, and as such can be observed by telescopes today, such as the Hubble Space Telescope. And then you get beautiful images like this one here, which is an example from the Hubble Ultra Deep Field Survey. This is when they would point the telescope at a seemingly empty patch in the sky, only to discover it's actually full of galaxies at high redshifts. Now, such an image provides us the abundance of galaxies as a function of their luminosity or magnitude, which is what we call the luminosity function. And then the question now is, what can this high redshift luminosity function tell us about the clustering of matter? So let's look first at how it's constructed. Very roughly speaking, the luminosity function, which I denote by phi here, can be separated into two parts. The first one is the halo mass function, which is mainly affected by cosmology. And the second one is the relation between halo mass and the magnitude of galaxies residing inside the halo, which is what we call the halo-galaxy connection, and it's mainly driven by astrophysical processes. Now, from the cosmology side, we have relatively good control over uncertainties, and that's because the process of how dark matter halos collapse and form is reasonably well understood, especially given the guidance that we have from embodied hydro simulations. So for a given cosmology, or better said, for a given dark matter model, we in principle should know what the halo mass function looks like. And then the name of the game is to try to figure out which of these halo mass functions fit our observed universe the best. Now, one of the main challenges here is that some of the cosmological effects could be mimicked by astrophysical effects, such as feedback processes. So ideally, we would like to separate these two contributions as much as possible. But it also means that we need to relate the mass of dark matter halos, something we cannot see, to the magnitude of galaxies, which is something we can observe. So how do we do that? So here I will give a broad overview of the current models that we have implemented in the code. So in our base model, we start with the assumption that the UV luminosity of galaxies at higher redshift is dominated by young stars. And this means that we can write down the star formation rate of such galaxies as a function of their UV luminosity using a certain correlation factor, kappa tilde, also known as the Kennicut relation. Next, we assume a certain functional form between the star formation rate and the halo mass accretion rate, which we call F star tilde. So how does F star tilde look like? So if you plot the ratio of stellar mass to halo mass as a function of halo mass, you'll find that it exists a peak somewhere around the mass of our Milky Way halo, somewhere around 10 to the 12 solar masses. For masses larger and smaller than 10 to 12 solar masses, star formation less efficiently, and that's because of a variety of bionic feedback processes, such as active galactic nuclei, supernovae, stellar winds, and so on. And a very simple function that captures this behavior is a double power law function. So we assume that this F star tilde is a double power law, then epsilon star, alpha star, beta star, and MC are all three parameters that we will marginalize over in our analysis. And then finally, we can use some accretion model that's calibrated to embody simulations to relate the accretion rate to the halo mass. And in this way, we obtain a one-to-one correspondence between M halo and MUV. And besides the space model, we've also included two other models. And these two other models are mainly there to check a number of our assumptions that we have made in the blue model. For example, the one in the red checks where a double power law between stellar mass and halo mass rather than the accretion rates makes any difference. The one in green tests this conversion factor between the star formation rate and the UV magnitude. Now, I want to emphasize here that this approach here, this method, is not applicable at the level of individual galaxies and halos. And it's because the magnitude of galaxies that we derive with this method only depends on the halo mass rather than the unique formation history of halos. So whatever we derive here really ought to be thought of as an average quantity. And with average quantity, we also have stochasticity involved. And the way we deal with stochasticity here is by treating this magnitude here as an average magnitude. And then we assume that the magnitude of galaxies inside halo follow a certain distribution with this average and with a width sigma MUV that we marginalize over in our analysis. So from now on, I will focus on the blue model. We can compute the luminosity function and obtain its dependence on the parameters in our normal, on the cosmological and astrophysical parameters in our model. So the first three panels show cosmological parameters affect the luminosity function. Those are sigma 8, the matter density parameter, and the scalar tilt. In principle, if you increase each of these variables, you increase the amount of halos and therefore also the amount of galaxies. So the luminosity function simply increases. The next four panels show how the astrophysical parameters change the luminosity function. Alpha star, beta star regulate the slope of the faint and bright end respectively. Epsilon star regulates the star formation efficiency. And MC simply tilts the entire luminosity function. Now, the main point of this figure is to highlight the degeneracies that exist between the cosmological and astrophysical parameters. So if we plot the sigma 8 curves on top of the epsilon star curves, we find that at the level of the luminosity function, increasing sigma 8, so having more galaxies, could be mimicked by making the galaxies brighter. And you see that while this degeneracy is not exact, it's still quite strong. Now, this is a picture at a single redshift only. And as it turns out, this degeneracy direction between cosmological and astrophysical parameters is slightly different at different redshift slices, such that when we combine data over different redshifts together, we can somewhat break this degeneracy and say something about cosmology. So far, this is a model, and now I will spend a few minutes on the data. So as I've told you before, the Space Telescope has been observing galaxies at high redshifts for decades now. This has resulted in two main catalogs. The first one is the Hubble Legacy Fields catalogs, and this one contains so-called blank field surveys. This is when the survey area is devoid of any foreground objects down to a certain threshold. The advantage of the legacy fields is that they have covered relatively large areas, and this means that they can have probed the mid and right end of the luminosity function. And because the survey area is devoid of any foreground lenses. In principle, this makes them also easier to model. On the other hand, you have the Hubble frontier fields, and they consist of observations of 6 cluster lenses, where faint background galaxies are magnified enough to become observable. And in this way, you probe the faint end of the luminosity function. But because you're dealing here with lensing systems, you also have to deal with lensing uncertainties. So there's a caveat in this regard. And besides real data, we have also mock data from the illustrative G hydro simulation. There are 3 different boxes that one can use. And this makes for an important cross-check because it allows us to verify our approach is actually able to extract the underlying cosmology. So in this particular work, we use data from the Hubble legacy fields and mock data from illustrative G. In both cases, redshift 4 to 10, we took into account cosmic variance, the dust extinction at the bright end of the luminosity function, and the Alko-Paczynski effect. And the Alko-Paczynski effect, the case here is that these references, they report the luminosity function at a certain cosmology, for a certain cosmology. And because we vary our cosmology parameters, we essentially have to recompute the volume element that enters the luminosity function at each step. And all of this is done in Galumi, which is our galaxy luminosity function pipeline. So we have implemented Galumi as a likelihood code in the publicly available MCMC sampler MontePython. And the reason why we did this is because it can readily be used in conjunction with other data sets, such as Planck CMB data or supernovae data. The current version contains the 3 astro models I mentioned earlier, contains different data mass functions, different dust calibrations, and we are planning to extend it further. And it's available at this link here. So now we have our model, we have our data, we have our pipeline, on a standard analysis and obtain a best fit plot. So here again, I show the luminosity function as a function of magnitude. The dots with error bars are data from the Hubble Space Telescope, and the salt lines are fits at these redshifts. So you see that, for example, at low redshifts, the data has smaller errors as compared to high redshifts. That's simply because at high redshifts, you observe fewer galaxies, and therefore the Poisson errors are larger. And likewise, you observe very few extremely bright galaxies. So the Poisson errors really blow up here. Now, importantly here is the top axis, which shows the corresponding halo mass at redshift 6 within our model. So you see that with current data, we roughly cover halo masses 10 to the 10 to 10 to the 12 solar masses. Now, such halos are very abundant today, but at redshift 6, they were quite rare. And rare halos are more vulnerable to changes in the clustering amplitude. And that's why we think that this probe might tell us something interesting about the clustering of matter. So what can it tell us? So let's start with the large-scale clustering amplitudes, sigma 8, which I show you as a function of the matter density parameter. The blue contours are obtained within our work. And we see that with current data, we are able to measure sigma 8 with an accuracy of roughly 15% at 68% confidence level. And you also see that with current data, our measurement is in fact a few less constraining than what you would obtain with other data sets, so cosmic share surveys, galaxy surveys, CMB data. But nevertheless, this is a new CMB independent measurement of sigma 8. It covers very different scales and redshifts than the data sets shown here. And future data will only further shrink this error. But that's really where the power of the luminosity function lies. So if we now look at the small scale clustering of matter, This figure here shows the linear meta-power spectrum as a function of wave numbers. The dots with error bars are measurements obtained from Planck CMB data, cosmic share surveys, galaxy surveys, and alpha surveys. And the black line here is the theory prediction for a cold dark matter cosmology. And going back what I said before, we still don't really know what a dark matter actually is. And one way in trying to get some, or trying to find some clues or hints, could be to try to understand what its small scale behavior is. So the question here is, what can the luminosity function tell us about the small scale clustering of matter? And the way we try to answer this question is by dividing the power spectrum into 4 separate bins. And then we vary the amplitude in each bin independently. In the first bin, we use Planck CMB data to constrain the amplitude. And in the other bins, so at small scales where Planck CMB data loses sensitivity, we have the luminosity function that covers this region. So we compute the meta-power spectrum at the center of each bin, run a standard analysis, so marginalize over astrophysical parameters, cosmological parameters, and we obtain these 2 new data points. And you see that with current data, we are able to reach scales of up to 10 inverse megaparsec, and we are able to measure the amplitude of the power spectrum with a precision of roughly 30% or so. You also see that current data is perfectly consistent with the cold dark matter paradigm. And this, of course, has consequences for alternative theories of dark matter. For example, if the dark matter is a thermal warm dark matter candidate, then you see that with current data, we are able to exclude such scenarios if the particle has some mass of order 1 keV. So to summarize quickly, the UV galaxy luminosity function is a rich tool to understand the physics of galaxy formation, both from the aspect of astrophysical effects, but also from the aspect of the clustering of matter. Current data allows us to measure the matter power spectrum up to wave numbers of roughly 10 inverse megaparsec, and this provides yet another new road to understand the small scale behavior of the dark matter. And I'll end with this updated summary plot, which now also includes the ranges that the UV luminosity function covers, which hopefully highlights its complementary nature to the other approach of it. With that being said, I thank you for your attention.
Thank you very much, Nash. Do we have questions for Nash?
I guess my question is, you're saying your sigma 8 constraint is what, like 50% or something like this. Is there a simple way for me to understand without an independent measurement of the mass of these galaxies? Why is this not degenerate with astrophysical? What is preventing you from changing the masses of these by a factor of 2 or whatever, and then making everything agree?
Yeah, like changing the astrophysics, you mean?
Yeah, I just don't understand how is it possible that because you're not using any independent measurement or estimate of the masses of these galaxies.
Mm-hmm.
So,
Mm-hmm.
you know, how is it possible that you can say something like?
Yeah, that's a very good question. So let me go back to. So, there are 2 parts here. Part 1 is we know what the halo mass function looks like. Like we basically fix what the halo mass function is.
Yeah,
and we know what its behavior is. Like we are dealing with pretty rare galaxies at the ratios we consider, and the halo mass function has some exponential decay. Now, for the halos that we cover, the halo masses of 10 to the 10 to 10 to the 10 to the 12 solar masses, this halo galaxy connection is a power law. So basically, in order to obtain back the observed luminosity function, we have something that looks like an exponential function, and we have something that we don't really know how it looks like, but this halo-galaxy connection cannot just have an arbitrary form. It has to give us back the observed luminosity function. And we know that the halo mass function has some exponential behavior, and this halo-galaxy connection means that it has to be something like a power law for the halo masses that we cover. So if you go to low enough masses, this becomes more tricky, but that's a different question. And at some point, you will be able to distinguish exponential behavior from a power law behavior. And that's really the reason why we're able to say something about cosmology. Does that answer your question?
Well, I just don't know how you know this function is a power law. So, like, for example, I can give you an analogy. If we were to try to model luminosity function at redshift 0, right?
Yes.
We now know that we have to put some feedback on the large masses because of these, feedback on the other, of the another type of the low masses because of, okay, we've discovered all of this.
Yes.
Right? Now, if we were doing this before having any information, we wouldn't have made up this story, which sounds a little bit ridiculous. I mean, too complicated. You are going out there, and we don't know anything. So maybe it's a complicated story. How you know, how do we know? It's just yeah. Anyway.
So yeah, I see your.
In other words,
I see your concern.
Your point, another way of asking a question is your point fits just on top of lambda CDM, so I'm happy about it. However, had you seen the 5 keV neutrino stuff, would I go out and say I'm happy about it? Say I don't believe anything. Probably I would say, oh, there's something he didn't include, and you probably would too, right? So you would start looking for things. What could it be? I don't know. Anyway, that's another way of saying the same thing.
I see your point. I think it's, I guess the main thing here is then how flexible are you with your astrophysical modeling and basically with the shape of the halo-galaxy connection. My argument is that basically current data, like a power law seems to fit current data very, very well. Will it be exactly a power law? Like if we improve the data and make the error smaller and smaller? Probably not. But at the current level of errors, which is like in the best case, like 20 to 30% in the data, this seems to work extremely well. And like you see, like these several approaches that people have like applied in this regard. We also have guidance from simulations that we can use in this regard. I do agree with you. It is not always a very straightforward thing, but I just want to say that like current data seems to work very well with a double power law function. And I think that's pretty much what everyone in this field is also using when it comes either to galaxies at higher ratios or 21 centimeter, because it's really the best we can do at this point in time with the information that we have. And of course, once things get, once we have better observations, better measurements, one can always like tune their model to account for things that were maybe not expected.
Thank you. Yeah.
There were also two questions, but Jay was first, if I...
I just had a quick question. So like regarding your plot where you compared these warm dark matter constant, like how is it compared to like Milky Way satellites or Lyman alpha? Just the values, I was curious.
So in reality, if you want to set bounds on like a thermal warm dark matter particle, you wouldn't really use this plot. You would use the mass function for a thermal warm dark matter cosmology, then run the entire analysis pipeline and so on. So I expect if you use the luminosity function, you would get something larger than 1 keV. As far as I'm aware, stellar streams, I think there was a paper from a couple years ago by the people at Amsterdam that found a bound of order 10 keV. Lyman alpha, I think around 5 keV. So I think the luminosity function is more competitive with the Lyman alpha. But you see that like we're dealing here with different sets of uncertainties and assumptions compared to Lyman alpha. So it's like, I think the main point, the main message here is like, this is like yet another addition to like probe the physics of structure formation.
Okay,
yeah.
Thanks.
There was a Changun also.
Yeah, I had two questions. One was the luminosity functions you get from the Hubble fields. Do those include cosmic variance?
Yes.
Okay.
No.
I was just
No.
surprised that they're quite small.
No, actually, they don't include cosmic variance. That is something we had to include ourselves in the analysis.
So wait, so do you include that in the final constraints that you showed? Because
Yes,
I imagine
yes,
that would
yes,
be
yes.
pretty okay.
Yeah, like as I. So these are the current corrections that we have applied to the data. So we basically like just grab it from and apply the corrections to it directly.
I see. And the other question that I had was regarding your galaxy halo connection. So the double power law that you showed, I think it's a bit misleading, I think, to say that all of the data fits that, because most of those constraints make pretty strong assumptions of the halo model. For instance, like half of them are abundance matching, and then the other half is some form of HOD fitting. So it's not like there are data points that line up perfectly with the power law. So have you tried to relax that assumption? And also, if you plot the UV luminosity constraints on this, do you get something more or less consistent with this?
So the first question is, we haven't really tried anything other than the double power law. The way we currently have checked the dependent results on the astrophysical modeling is more by looking at the redshift evolution of these astrophysical parameters. So for example, many references keep all these astrophysical parameters fixed as a function of redshift. Well, we tried many different locations, really, and then like looked at what fits the data and what doesn't. But like considering something else than a double power law, no, that's something we haven't done yet. So it would be very interesting to, of course, consider that in future works. With regards to like whether we have made a similar plot for the luminosity function, as in like we have plotted our own curve here. Let me think. No, the closest plot we have of the galaxy connection is this is really, it's not really comparable with what you asked, but like we have no, like in principle we haven't plotted the equivalent of the double power law. it's a bit difficult to do that in the 3 different models because you can't really derive in all 3 models. So like if you go to this plot, so this plot shows particularly m star divided by m halo. And for example, in our model 1, you don't really have m star, you have m star dot. So like one would have to look at model 2 in that regard. So it's possible, but we haven't done that.
Okay. All right. Thanks.
Okay, so I think we are 10 minutes